Welcome to homework.
So for problem 15.191, we know that the disk A of radius r small of the drawing is free to rotate about the horizontal rod of length r there, and which rod in its turn is connected to the vertical shaft OC, which rotates with an angular velocity vector omega 1, which is for a rotation clockwise if we see it from the positive y direction. Now, disk B is stationary in contact with disk A, forcing this way disk A to rotate due to friction. Given these, we want to calculate the angular velocity of disk A and the angular acceleration of disk A. For the first task, let's find firstly the angular velocity of disk A with respect to the rotating rod away. It's easy to find it if we think that necessarily, let's make a drawing, necessarily that the arc that is created by the edge A of the rod OA is the same path that the edge of disk A travels upon. What this means that the linear, let's use another color, that the linear velocity of the edge of disk A is exactly the same as the edge of rod OA or point A. Okay, this translates to that the angular velocity of disk A relative to the rotating rod times times the radius of the disk, which gives the linear velocity of the edge of the disk, equals the product of the angular velocity of the shaft OC times the length of the rod. Therefore, very easily, we have the magnitude of the angular velocity of the disk A with respect relative to the rotating rod. And someone can easily see that from the drawing, we can say that the direction of this rotation is counterclockwise if we see it from the center or from the origin or from point O of the system. It goes like this, counterclockwise. Okay. Given this, we can calculate now the angular acceleration of disk A with respect to the fixed frame now. And in order to do this, we need to add the angular velocity of the shaft or the rod plus the angular velocity of disk A relative to the shaft or the rod. We know this one. This is just omega 1 j hat. But what about this one? We know its magnitude. Its magnitude is just omega 1 times r over r small. And we know its direction counterclockwise if we see it from the origin. And if we check the drawing, this translates to a direction towards the positive z-axis. And this is momentarily the angular velocity of disk A with respect to the fixed frame. Now for the angular velocity, for the angular acceleration of the disk A, we need to choose a rotating frame, and for convenience, let's choose a rotating frame that rotates with the shaft. So the angular velocity of the rotating frame is exactly the same as that of the shaft or the rod, vector omega 1. And this is in order to use this relation I denoted the rotating frame with prime indices. And this is the rate of change of the angular velocity relative to the angular velocity of the disk A relative to the rotating frame, and this is the angular velocity of disk A relative to the rotating frame. An observer now on this rotating frame will see the disk A rotating exactly in the direction that we described before. But the observer won't see any rate of change of this angular velocity. Angular velocity is constant, doesn't change with time. And if we replace this gives us finally this result for the angular acceleration of disk A. Two comments: I haven't used any prime indices because we are working under the assumption that momentarily the rotating frame and the fixed frame that they coincide. And another thing, I hope it is clear that this result is consistent with the units that the angular acceleration takes. Usually we use radians per second